Good afternoon, David De Los Reyes. My topic for this afternoon is application of integration on the solution of or the solution for computing plane areas. Okay, let's proceed. The topic is plane areas, integral calculus. This is now an application of our knowledge of the integration evaluations, okay? Plane areas. Rectangular coordinates. Rectangular coordinates meaning we got the y-axis and we got the x-axis. Okay? Okay, from the figure on the Cartesian coordinate system, this should be y higher equal to a function of x. This graph here, or this curve, the first curve, the equation of that will be y with the subscript h function of x. The lower curve, y lower p of x. This is the first curve. This is the second curve. The problem is asking for the area, okay, bounded by these two curves with the given limit x1 up to x2. The problem is asking for the area, the shaded area with the color red. This area here. The one with the color red by using integral calculus. So as you can see, it's an irregular figure. Okay? I'll bring out the general formula for taking the area between two curves with the limit x1 to x2. Find the area of this with the limit from this x here up to this x, meaning from x1 to x2. We are given the curve up. Equation number 1 is y higher is function of x. This one, the upper one. The lower one is y lower is p of x. It could take any form. It could be a straight line. It could be a parabola. It could be a hyperbola. It could be an ellipse. It could be anything. Anything that's what you call this, expressed as a function of x and p of x. Anything imaginable for the value of the first curve and the second curve. Okay, I'll bring out the general formula on how to take the area between these two curves between the limit x1 to x2. Oh, simple. We make a vertical slice over here. So if I will bring out the vertical slice, okay, I will take a vertical slice. The thickness of that will be dx. Okay? And the height is equal to y higher minus y lower. Why y higher minus y lower? This point here is y lower. This point here is y higher. Right? So this height here, the height of the slice will be y higher minus y lower. So I place it here. The height of the differential slice is y higher minus y lower. The area represented by the vertical slice is a differential area. So if we take the area of this, assume for the meantime it is a rectangle. Okay? So the area of this will be this width here times this height. So differential area is actually y higher minus y lower times dx. It is this. Simple, right? And the real problem, y higher minus y lower will be a variable thing. It could be a constant, it could be an algebraic function which is complicated. It depends on what is given. So in general, by using vertical slice under rectangular coordinates or Cartesian coordinate system, the differential area, the area of the thin slice here is y higher minus y lower times dx. This y higher minus y lower times dx. With the limit from x1 equal to the lower limit, x2 will be equal to the upper limit. With reference to 0, 0, this is x1. With reference to 0, 0, the upper limit is actually x2. Okay? So the range of the area that is being asked is from x1 to x2. So the limit is actually x1 to x2. x1 is the lower limit, x2 is the upper limit. What's the significance of this, guys? That was our topic the last time around under the so-called evaluation of definite integrals. If you are integrating and you are given in a lower limit and upper limit, you are evaluating a definite integral. So under plane areas, okay, it's an application of definite integral. Okay, I will give you an example. Derived by integration the general formula for finding the plane area of a square with side S. The designation of the length of the side of the square is S. Okay? Actually, even at the start, okay, we know that the area for taking the area of a square is actually side square, right? So by using integral calculus, we will derive this one. So actually, the formula area equal to side square for any square emanates from integral calculus. Okay, let's bring out the solution. To bring out the solution, you must know analytic geometry. Okay? Draw your y-axis, draw your x-axis, the horizontal and vertical, right? Then try to bring out the figure square on the Cartesian coordinate system. For a square, we know the figure is something like this, right? This is S and this is S. So try to place it on the Cartesian coordinate system. Okay? The first corner is at 0, 0. The second corner is at S equal to 0. This is S and Y is actually 0 because it is on the x-axis. For this point here, X is 0 and the value of Y is S. This is S. This is Y and that is S. Okay? For the fourth corner, the location of this, if we try to graph it, okay, it will be S and S. Meaning this is S and this is S. So the designation of it under the Cartesian coordinate system will be S and S. Okay, so we figure out already the square on the Cartesian coordinate system. If we try to use vertical slice, this will be the vertical slice. That's the vertical slice. The one I discussed a while ago. The thickness will be dx. Okay? And what is this height? Oh, luckily for a square, height is equal to S. Okay? The height is S, and we are lucky it is constant. It's not variable. Right? So if we try to bring out the equation of this, it is actually a straight line. The equation is y is equal to S. The equation of the bottom line, the horizontal axis, y is equal to 0. Okay? So if we try to go back here, differential area is actually y higher minus y lower times dx. We are just following this. Y higher is S. This is y higher, it is S. Okay? This is y higher. Y lower is actually the ordinate at this point here. Y lower is actually 0. So this should be y lower is 0. And what will be the limits? The problem is asking for the area of the square from this point here up to this point. X here is actually 0 and x here is actually s. So x1 will be 0, x2 will be s. So we now bring out the formula. We designate already the lower and upper limit. It's just a matter of substitution by following this. Therefore, differential area now will be equal to, we are following this. Y higher is S. The equation of the top straight line. And the equation of the lower straight line is actually 0. The equation is y equal to 0. The equation of the horizontal line is y is equal to 0. This is minus 0 times dx. Okay? Therefore, differential area for a square will be s dx. As simple as that one. To bring out the general formula for a square, try to integrate both sides. The integral of differential area, we are integrating this one, will be equal to the integral from 0 to s. Lower limit is 0, upper limit is s. It is from 0 up to s. To take the total area of the square, the limit of x will be from 0 to s. Right? So this is 0 to s of s dx. This is now the integration part. So whatever integration that will come out, apply it. We are now through with the different integrations. Okay, s is constant. We bring it out. So area will be s, the integral from 0 to s of dx. Okay, the integral of dx is just x, right? For a square. Therefore, area now will be equal to s. The integral of dx is x with the limit from 0 to s. Okay? We are given the lower limit, we are given the upper limit, just substitute. Therefore, area will be equal to s times the quantity s, the upper limit, minus the value of the lower limit, which is 0, close bracket. Okay? But this is 0. So what will come out will just be simply times s. Okay? S times s is s squared. And that is now the general formula for taking the area of a square. That's where the formula area equal to s squared emanates. It is from integral calculus. So for a square, okay, if you are sure that the figure is a square, to take the area, just take the square of the side, and that's the area. Area for a square that was derived from integral calculus right now, area is equal to s squared. That's it, guys. It's easy if you know integral calculus. Evaluation of integration. Because upon reaching application, if you don't know how to integrate, you cannot solve the problem. So actually, before the start of integral calculus, I said to you guys, in order to familiarize or to solve problems on the application problems under integral calculus, you should know all the integration techniques. That's a must. Okay, good afternoon, Los Angeles.